Now, the latest development from Google is that it describes a state-of-the-art quantum computer chip. Guys, it's finally happened. Google has introduced a quantum computing chip that transforms what we know about computation, and it takes 5 minutes for them to solve a problem that would currently take supercomputers 10 septillion years to complete. What if I told you that scientists just made particles 100,000 times heavier than an electron vanish through solid barriers without breaking them? At CERN's Large Hadron Collider, researchers have shattered our understanding of physics by observing quantum tunneling in massive particles. This breakthrough could lead to ultra-fast computing, near-instant energy transfer, and even new insights into the fabric of reality itself. Stay with us to explore how this discovery might revolutionize technology, space travel, and even our grasp of the universe, because this isn't just theory anymore. It's happening. Breaking the quantum barrier. Quantum tunneling is a phenomenon where subatomic particles, such as electrons, pass through energy barriers that, according to classical physics, they shouldn't be able to cross. Imagine a ball approaching a hill in the macroscopic world. If the ball lacks sufficient energy to surmount the hill, it will roll back. However, in the quantum realm, there is a probability that the ball can appear on the other side without climbing over, as if it tunneled through the hill. Traditionally, quantum tunneling has been observed in particles like electrons. However, recent experiments at CERN's Large Hadron Collider have taken this to an entirely new level by demonstrating quantum entanglement in much larger particles, specifically top quarks, which are approximately 100,000 times more massive than electrons. This observation was reported by the ATLAS and CMS collaborations in September 2024. This discovery has significant implications for our understanding of quantum mechanics. The Heisenberg uncertainty principle posits that one cannot simultaneously know both the exact position and exact momentum of a particle. However, the entanglement observed in these experiments suggests that certain quantum behaviors can manifest in larger particles, potentially challenging or refining our current interpretations of quantum mechanics. Furthermore, during these experiments, researchers detected subtle fluctuations in the local gravitational field, an observation not previously seen in quantum experiments. This could provide insights into the elusive theory of quantum gravity, which aims to unify quantum mechanics with general relativity. The notion of quantum gravity has intrigued physicists for more than a century, as it could help explain the fundamental structure of the universe at the smallest scales. To put this into perspective, consider a real-world analogy. If a tennis ball were thrown at a solid brick wall, classical physics dictates that the ball would simply bounce back. However, in the quantum world, there exists a small probability that the ball could appear on the other side of the wall without breaking through it. This is precisely what CERN's experiment has demonstrated, but on a scale never before observed. The ability to manipulate this effect in larger particles could redefine the limits of what is physically possible. Confirmation of quantum entanglement in larger particles opens up new avenues for technological advancements. Potential applications include the development of faster computing systems, more efficient energy storage solutions, and advancements in quantum communication technologies. Imagine computers that operate at speeds exponentially beyond what we currently have, or batteries that charge in an instant by leveraging quantum energy transfer. The potential is staggering. In summary, CERN's recent experiments have not only expanded our understanding of quantum phenomena, but also hinted at the possibility of bridging the gap between quantum mechanics and gravitational theories. The findings could lead to groundbreaking technological innovations that might redefine how we interact with the physical world. The discovery of tunneling in larger particles is not just an advancement in theoretical physics, it is a glimpse into a future where the impossible becomes reality. But what if this quantum tunneling effect isn't just limited to subatomic particles? What if it could be harnessed on a larger scale, even beyond what CERN has demonstrated? Imagine a world where solid objects pass through barriers, where energy is transferred instantly, and where the very fabric of space bends to quantum manipulation. Scientists are now asking the big question, could quantum tunneling unlock new frontiers in energy, space travel, or even human biology? The implications go far beyond physics textbooks. They could redefine the very nature of reality itself. Tech that sounds like sci-fi Imagine a world where the boundaries of science, fiction blur into everyday reality. At the heart of this transformation lies a phenomenon called quantum tunneling, a concept that, while complex, holds the potential to revolutionize numerous facets of our lives. Let's embark on a journey to explore how this quantum marvel could reshape energy, computing, medicine, and even space exploration. Picture a future where charging your smartphone or electric vehicle takes mere moments instead of hours. This vision could become a reality with the advent of quantum batteries. Traditional batteries rely on the slow movement of electrons through barriers, but quantum tunneling allows electrons to instantaneously pass through these barriers, enabling ultra-fast charging times. Researchers are actively exploring designs for these quantum batteries, aiming to surpass the capabilities of current energy storage technologies. Major technology companies are keenly interested in this development, recognizing its potential to provide clean and virtually limitless energy solutions that extend beyond the capacities of solar or wind power. Envision computers that operate at room temperature, performing calculations in seconds that would take today's machines millions of years. Currently, quantum computers require extremely low temperatures, close to absolute zero, to maintain their delicate quantum states. However, recent breakthroughs suggest that room temperature quantum computing could become feasible much sooner than anticipated, potentially within the next 5 years. This advancement would enable machines to solve complex problems rapidly, accelerating progress in fields such as drug discovery, cryptography, and the design of novel materials. Companies like Google are at the forefront of this research, developing quantum chips like Willow that have demonstrated unprecedented computational capabilities. Imagine medications that can navigate directly to specific areas within the body, such as the brain, without invasive procedures or adverse side effects. Quantum tunneling could facilitate the development of drug delivery systems capable of crossing biological barriers like the blood-brain barrier, ensuring that treatments reach their intended targets with precision. This approach promises to enhance the efficacy of therapies for neurological conditions and reduce systemic side effects, marking a significant leap forward in personalized medicine. Consider spacecraft powered by reactors that harness energy from the quantum vacuum, enabling missions to Mars and beyond. Quantum tunneling might make it possible to extract energy from seemingly empty space, providing a continuous and reliable power source for long-duration space voyages. Additionally, this technology could lead to the development of advanced propulsion systems, reducing travel times and expanding our reach into the cosmos. Think of communication systems that are impervious to hacking and radar technology, capable of detecting even the most stealthy objects. Quantum tunneling underpins the development of quantum communication networks, which utilize the principles of quantum mechanics to create theoretically unbreakable encryption. Furthermore, quantum radar systems could detect objects with unparalleled accuracy, enhancing surveillance and defense capabilities. Experts anticipate that practical applications of these technologies could emerge within the next decade, transforming the landscape of national security. The implications of quantum tunneling extend far beyond these examples, touching upon various aspects of technology in daily life. As researchers continue to unravel the mysteries of quantum mechanics, the line between science fiction and science fact becomes increasingly blurred. We stand on the cusp of a new era where the once impossible becomes possible and the unimaginable becomes reality. But the real mind-bender is what this all means for our understanding of reality itself. If quantum tunneling can do all these incredible things, charging batteries in an instant, revolutionizing medicine, and even powering space travel, what else might it be capable of? The implications stretch far beyond technology and into the very foundations of physics, shaking up the universe's rules. Here's where it gets really wild. This experiment might rewrite how we understand the universe itself. For 100 years, physicists have been stumped trying to mix quantum mechanics, the rules of the tiny, with general relativity, the rules of the huge, like stars and gravity. They don't play nice together, but CERN's results suggest the line between these worlds isn't as solid as we thought. When those bigger particles tunneled, they didn't just break quantum rules, they hinted at something bigger. During the test, instruments picked up an extra burst of energy that shouldn't have been there. It's like the particles gained power out of nowhere, which goes against the conservation of energy, a rule we've trusted forever.